Okay, quality assurance. Quality assurance is designed to ensure that a CT system is producing the best possible images using the minimum amount of radiation, right? And it provides a method for systematically monitoring the system's performance. We're going to do QA every week or every day, depending on what our criteria is. The ACR then is going to come in and do like yearly QA sessions. And the responsibility is typically shared between CT technologists and their medical physicist. The tests that make up the program need to be performed on a regular basis. A lot of times we have daily system tests that the CT scanner will just put itself through. You initiate the test and it does its dose check, or it does its phantom check test. And those are recorded typically on the system, or we may just document it separately from the system. We may write out and make some screenshots, make some measurements, and write down what our measurements were. And then those will be fed into specific guidelines. So here's those this QA phantoms that we use for a lot of these tests. We love our QA phantoms. We want to be very gentle with them. Don't be joshing around and playing football with them. Most are designed with a bunch of components inside them so that a single phantom can be used for a number of different scanner parameters, right? So this phantom here, we can see it's done a spot test, it has a water test, it has another water test, and then it has some kind of spatial resolution test. All of those are stair-stepped into that phantom. So if we look right here, we see different lines here, and each one of those is going to be different tests, okay, that the phantom can do. Here's a spatial resolution test. This is one of the most common tests that we do. We're going to evaluate between different pairs of lines. And this phantom contains groups of lead strips, and then the minimum amount of lead strips that can be differentiated on a given slice are what we're measuring, right? So we may even place like an ROI on that. Can I visually read that? Can I differentiate? Can I see that that's 4 or 5 lines, right? These are the questions we're asking ourselves and making our notes in our documentation. Versus up here, can I clearly differentiate those lines? Does it have an appropriate spatial resolution? This dot here is going to be like a baseline kind of thing. So we may do baseline ROI placements out here in the water as well as right here, right? And those will give us like a baseline. Was the scan initiated with appropriate technique? So going back to contrast resolution, we're going to evaluate this with a phantom that contains objects of varying sizes. Just like with those lines, they have different spatial spacing between those lines. We can also make phantoms that have a bunch of different sized objects. And the phantom is then scanned at different mass settings, and the most common method requires for an observer to detect the objects. I'm going to actually look at the picture. Can I tell that that object is there or not? Okay, slice thickness accuracy. We're going to measure this with a phantom that includes a ramp or a spiral or a wedge, and then as we scan through that phantom, we're going to be able to tell, for instance, was this distance appropriate? Is it actually, I told it to scan 2.5 millimeters. Did it actually scan 3 millimeters? Right? Did it move too much? How accurate is it in recording and executing slice thickness? Laser light accuracy. I'm going to turn on the lasers and line them up to the phantom and see if they converge at isocenter. Because a lot of times what happens is eventually the lasers go a little bit out of whack. And now I'm not truly being able to zero the patient to that isocenter. And there's typically different kinds of design things that are made specific for that vendor, for that manufacturer, for measuring that. Noise and uniformity are measured using a water phantom, and typically we're going to have some kind of standard deviation numbers. We're going to throw an ROI on that, and we want to be within a certain range. Uniformity refers to the ability of the scanner to yield the same CT number regardless of the location of an ROI. So if we have a water phantom, it's just a homogeneous area, and we put ROIs all over the water phantom, they should be measuring close to the same levels, right? Linearity. So this is going to be the relationship between CT numbers and the linear attenuation values of the scanned object. So we can actually use a phantom and we know specifically what its linear attenuation value is. So we know specifically what the Hounsfield units should be measured at that place. We can put a series of different kinds of linear attenuation values within the phantom, scan that, and then look at our Hounsfield units on our scanner. How close were we to what those objects actually are? Radiation dose. So, technologists need to be really acquainted with all the factors that affect radiation dose in the patient, and we need to be able to provide safety instructions to the patient about how radiation dose works within the scan room. In addition to that, when we work with the medical physicists, they will be coming in and measuring the dose levels with a special kind of dose phantom and special kind of ion chamber that can be scanned by the scanner. It can accurately tell us how well the dose is being used to produce those images. So, laws require dose measurements for each facility's CT scanner, and they need to be performed by the medical physicist. And then measurements are obtained using some kind of standard head and body CTDI phantom, right? And again, that pencil ion chamber. And then we compare those doses back to what's in the literature, right? Another really important part of reporting dose goes back to CTDI again, and I believe it's called DLP. There's going to be numbers that are generated by the scanner. We'll take a screenshot of those numbers and normally include those with the images in packs because they are an accurate way to report what the patient's dose was for that scan. Image artifacts. This is also in task 23. So anything that appears on the image that is not present in the object itself, we're going to call an artifact. And there's a bunch of different kinds of artifacts. This is kind of the remainder of this lectures. We'll talk about how those artifacts, what they look like and what caused them. They're typically physics-based, patient-based, like with metal or motion, or equipment-induced. There's certain kinds of artifacts that it's just because the equipment is not quite calibrated right, so it's producing an artifact. Beam hardening artifacts. These are caused again by that polychromatic nature of the X-ray beam. That goes back to the X-ray beam is like a rainbow. It's got a bunch of different quality X-rays within it. The kilovolt peak is the maximum amount, but then there's a spectrum of X-ray energies underneath that. And then as the X-ray beam passes through the object, the weaker energy is going to get attenuated, the higher energy is going to go through, and it's going to harden the beam. And that beam hardening has to be accounted for by the system. So CT systems minimize beam hardening in 3 ways. They use initial filtration. So on the tube side, there's going to be some kind of aluminum equivalent that's removing the really weak X-rays out of the X-ray tube before it even goes anywhere near the patient. Then there's calibration corrections. There may be things that we need to calibrate within the machine to account for that. And then there's actual software that there's algorithms that we can apply to the data that reduce that artifact. So here's an example of beam hardening artifact. At the base of the skull, we see these streak lines right here across the base of the skull where it's darker. There's not like a nice uniform attenuation throughout that area of soft tissue. Again, the beam has been hardened by the skull bones. Partial volume artifacts. This occurs when one type of tissue is contained within a voxel. More than one type of tissue is contained within a voxel. And the best strategy to reduce these artifacts is to use thinner slices, right? So what this is saying is, imagine we've got 2 voxels right next to each other, right? But within this voxel, we've got something within the tissue that's like half in, half out of the voxel, right? So this voxel is going to read a certain number that's not quite right compared to if that dot was right in the middle of it. Okay? So it's partially volumed. It's interpolated the information, and we've lost some of an accurate assessment of the attenuation there. An example of that is going to be a gradient edge artifact. This is a very faint thing, but we can see there was an abrupt translation between the stomach and the barium and air in the stomach. Let me turn on my little thing. So barium and air in the stomach, And then as the beams were moving over here into the liver, we have this faint edge of trace there, right? Very, very faint artifact, but it's a streak artifact or a shading area arising from irregular shaped objects that have pronounced differences in density, right? So the air and the barium in the stomach were much different than the Hounsfield units in the liver. So now it's shaded some of that difference into the liver. Motion artifacts. Just please tell your patient to hold still, or you're going to get pictures that make them look like an evil ghost, right? Metallic artifacts are going to streak the images, especially if they are within the scan field of view. And this is significant because it might be outside of the display field of view, right? It might be outside of the area that I'm looking at on the picture. There's a metal block over here, right? But because it was within the scan field of view, now I have a metallic artifact. And the best way we can get rid of it is to ask the patient to take off their earrings. You know, take off your crazy piercing that no one should ever see, right? Don't tell me it's hard to take off. You shouldn't have put it there to begin with, right? It's going to streak your pictures. If it's not removable, then we may need to angle the gantry, right? Y'all don't, I don't think in PET we have that option. Okay, out of field artifacts. Anytime the anatomy extends outside the selected scan field of view, we might get a streak artifact just because the scanner is no longer correctly accounting for what it's seeing, right? And so it's going to be a streak within the shaded area. We can see we've clipped anatomy on either side of this abdomen. If we just opened up the scan field of view higher, we're not going to get these streaks. Okay, 4 more slides. This one's really critical. Ring artifacts are caused by imperfect detector elements. The scanner is getting old, right? And so when we scan the water phantom, this is a water phantom here, we're going to get concentric circles or rings within the water phantom. This is all a uniform density, right? But now we have ring-shaped artifacts inside of it. So we may need to either replace the scanner detector elements or possibly just recalibrate them. Tube arcing. So anytime we have an electrical surge within the X-ray tube, we can have a high voltage arc, right? And there's not going to be a specific pattern to these appearances. They're going to be pretty minor unless there's a real severe problem, and typically that would have triggered an error message and require some kind of service call. 2 more slides. Spiral and cone beam effect. This is only with a helical scan, and it's going to be attributed to the interpolation and reconstruction process. So it's going to result in subtle inaccuracies in the CT number, and it can be easily misinterpreted as a disease, right? These are avoidable by using a lower pitch number. So if we're starting to see these kind of inaccuracies in our scanning protocols, we may need to think about bringing our pitches down closer to 1, right? So helical multi-detector CT systems may also experience windmill artifacts, and this is going to be caused by the cone-shaped rather than fan-shaped beam. And it's going to appear as streaks that look like a windmill, right? And it's going to be more pronounced with outer detector rows. So this explains why some of the 64-slice scanning protocols use only half of the detectors, right? As they're trying to reduce this artifact. Okay, that's it. Thank y'all.